So this is part 2 of Chapter 1 for Bio 1005. We just discussed a simple example of the scientific method with a woman with a broken flashlight. A more complicated one would be a case study kind of situation. So this time we're going to look at a case study, and they're going to look at how trans fats affects if that could stay in your body and if it could cause a heart attack. So if we look here, dietary fat comes in different forms. Trans fat is actually a non-natural form that was produced starting, I think, in the 1950s or so. They added hydrogens to oils to make them trans fats. So trans fat adds texture, it increases shelf life, and it's also cheap. So they did a study of 120,000 female nurses. So that's one of the things we look for when we're looking at a scientific study. What is our sample size? So if we have 120,000 nurses, that's a pretty good sample size. And they found in this study that high levels of trans fat, if you ate these artificial fats, it could double the risk of heart disease. So if we go back to our scientific method, we always start with the observation. So the observation was that human body fat contains traces of consumed fat that you have eaten. And then they asked the question, would the fat tissue of heart attack patients be different from a similar group of healthy patients? And then they formed the hypothesis that healthy patients' body fat would contain less trans fat than those who had had a heart attack. The researchers set up an experiment. They determined the amounts of fat in here. Our sample size has gotten much smaller. So they did 79 patients who had had a heart attack. That's still a pretty decent sized number of people. And they compared those patients to the data for 167 patients who had not had a heart attack. So we've got a sample size of 167 without a heart attack, 79 with. We also want to keep some other things controlled. So what we would want to make sure that these patients were in the same age group. Say we wouldn't want to have 20-year-olds being compared to 75-year-olds. So that's one of those controlled variables where we're trying to keep something the same. Everything is the same about these patients except that one group had a heart attack. So the results showed significantly higher levels of trans fat in the bodies of people who had had a heart attack. Since this study and others, they have tried to phase out these trans fats. A lot of fast food restaurants, McDonald's, Kentucky Fried Chicken, they don't use trans fats in their frying anymore. So we talked in part 1 about how a hypothesis is actually an educated guess, and how in common language people use the word theory all the time, and the scientific definition of the word theory is much different from how people talk about theory in everyday life. So a scientific theory is going to be a confirmed, comprehensive explanation supported by abundant evidence. These scientific theories become widely accepted only after they are supported by an accumulation of extensive evidence, like centuries or decades of evidence. So on your study guide, the last page, it says, which is a bigger deal, a hypothesis or a theory? And here you're doing the scientific definition, so a theory is a much bigger deal than a hypothesis. I want you to briefly explain the difference between a hypothesis and a theory, and then be able to tell me, is a scientific definition of theory the same thing as the common usage of the word theory? I really want you to understand that. Some people will argue against evolution, saying it's just a theory, but those people don't understand that in science, theories are a big deal. So here are some examples of important scientific theories. We've got the theory of evolution, Charles Darwin, the theory of relativity. Thank goodness I don't have to teach that. From Albert Einstein, the theory of gravity, Newton and Einstein, and the theory of a heliocentric solar system. So that, big long words just to mean that the sun is in the center of our solar system and the planets revolve around it. So the culture of science, scientists really routinely question each other's work. They publish their research in peer-reviewed journals. They present their work at meetings. They often try to repeat each other's work to verify the results. And this last slide is some definitions for students in my face-to-face classes. It also may be useful for my online students. These words are going to come up over and over again as we design experiments or in the online ones. What is a control? A control is going to be the unchanged group that we compare to. If you do an experiment without a control group, you can say nothing about your experiment. So we have independent variables and dependent variables. So independent, you can think in is the input. This is going to be the one changed by the scientist. And the dependent variable, this is going to be how are you seeing that there is a change? So this is going to be your observations or your measurement to see how it responds to the independent variable. So let's say we were doing an experiment where we had two groups of plants. One was unfertilized and the other was fertilized. Our independent variable, what we were changing, is going to be adding fertilizer. Our dependent variable would be how tall, measuring how tall the plants grew. So you also want to be aware of the term controlled variable, which controlled variable is different from a controlled group. Controlled variable are going to be the parameters that stay the same. In an example of an experiment, if we had fertilized plants versus unfertilized plants, the controlled variables would be the same light, the same temperature, the same type of plant, the same soil. So those are the things that you want to keep the same in an experiment. And the only thing that's changing is going to be the independent variable.